So it's practice problems. This is the first question for practice questions. It's asking us to determine limiting and excess reagents and determine how many moles of limiting reagent there are. So first step is to start with a balanced reaction. And again, you're going to be writing in states. Writing water as HOH helps people see that there's an hydroxide ion here. We are actually all balanced throughout here, and so now we're going to start by writing in our givens. We have 50 mils of 1.25 molar hydrochloric acid, and we have 75 mils of 1.0 molar potassium hydroxide. First steps first, we have to figure out the reactants for each reagent. And we end up with 0.0625 moles of HCl. And we end up with 0.075 moles of potassium hydroxide. The next step that we need to do is we need to look at the mole ratio. So reading left to right, we have 1 mole of hydrochloric acid in the reaction, and we have 1 mole of potassium hydroxide. Looking at the calculated values, 0.0625 over 0.075. Looking at the rate of consumption for the reagents, we see that 0.0625 is less than 0.075. Therefore, the limiting reagent is hydrochloric acid. With 0.0625 moles. Next question. Or not. One 1.25 grams of sodium hydroxide is reacted with 300 milliliters of 10.5 moles per liter nitric acid. First step that we have to do, we have to create a balanced reaction. Again, you're going to be making sure that you're putting in states. And we can see here that this is a 1 to 1 to 1 to 1 ratio. Next step is to write in our givens. We have 125 grams of sodium hydroxide and 300 milliliters of 10.5 moles per liter of nitric acid. Third step is to figure out the number of moles for each reagent. We're going to divide 125 grams by the molar mass of sodium hydroxide. And then we need to figure out the number of moles for nitric acid. From here, we need to look at the mole ratio. From our reaction equation here, we have 1 mole of sodium hydroxide and 1 mole of nitric acid, and then our calculated values. Looking at the rate of consumption, we see here that 3.125 is less than 3.15. Therefore, sodium hydroxide is the limiting reagent. This one here says 5 grams of magnesium solid is reacted with 7 grams of hydrogen chloride gas with added water. So here we see the first step, again, is to write out our balanced reaction. Sorry, that should be water. Oh, sorry. The main reaction is going to be this. So we have 2 hydrogens here. We need 2 hydrochloric acids, 2 chloride atoms on this side, and we have 2 chloride atoms on this side. So now we're balanced. The first thing that we need to do after that is calculate or write down the information given. And we do this by, we're going to take 5 grams of magnesium solid, and we're going to divide it by the molar mass of magnesium. And then we're also going to figure out the number of moles for hydrochloric gas. And divide it by its molar mass. The third step is to look at the mole ratio. So we have 1 mole of magnesium, and from our reaction we see that we have 2 moles of hydrogen chloride gas, and our calculated values are as such. When we look at the rate of consumption, we see that 0.192 is less than 0.412. Therefore, the limiting reagent is going to be hydrogen chloride gas at 0.192 moles. D, we're looking at 100 milliliters of 0.5 moles per liter hydrochloric acid is reacted with 50 mils of 1.0 moles per liter potassium hydroxide. First step is to create a balanced reaction. And again, I'm writing water as HOH so that you can see it when we're balancing out hydroxides. In this particular case, we're completely balanced with a 1 to 1 to 1 to 1 ratio. So the next step is to write in a list of all of our knowns. And then our third step is to calculate the number of moles for each reactant. So we've got 0.05 moles of, this should be, would help if I put the right information down. .5. Okay, so 0.05 moles of hydrochloric acid, and when we're looking at our potassium hydroxide, we have 1 molar times 0.05 liters equals 0.05 moles of potassium hydroxide. Looking at the mole relationship for the reactants, we have 1 mole of hydrochloric acid and 1 mole of potassium hydroxide, 0.05 moles over 0.05 moles. And actually, what happens is, in this particular case, they're equal. So we just say that there is no limiting or excess reagents. Excuse me, hydrochloric acid and potassium hydroxide are going to be completely consumed in this example. Okay, phosphoric acid is reacted with sodium hydroxide. What is the maximum mass of water that can form? This maximum mass of water is the way that you're going to interpret that this is a limiting reaction question. So starting with balanced equation, H3PO4, that should say and HOH. So we have 3 sodiums here. We need to put a 3 in front of our sodium hydroxide, which means that we have 3 hydroxides. So if we put a 3 in front of the water, leaves to 3 hydrogens, and we see over here that we have 3 hydrogens. So now we're balanced at a 1 to 3 to 1 to 3 ratio. Next step is to write our givens in. Phosphoric acid, 100 mils, 0.10 moles per liter sodium hydroxide, and we're looking for the mass of water. So next step is to calculate out the number of moles for each reactant. I'm going to take the molar concentration and multiply it by volume to get the number of moles for phosphoric acid. Yep. And we're also going to do the same thing for sodium hydroxide. 0.10 moles per liter times by 0.1 liters is going to give us 0.001 moles of sodium hydroxide. The next step is to look at the mole relationship. We have 1 mole of phosphoric acid to 3 moles of sodium hydroxide in the reaction. And we've calculated out that we have 0.01375 moles of phosphoric acid to 0.001 moles of sodium hydroxide. We're looking at the rate that it's being consumed, and so we see that 0.001 is going to be less than 0.04125. Therefore, sodium hydroxide is our limiting reagent. Now that we have the number of moles and we know which one is the limiting reagent, we can now go ahead with the rest of the steps that typically follow stoichiometry. So we're going to look at 0.001 moles sodium hydroxide, and we're going to look at our ratio between our given and our want. Our given is 3 moles, and our want is also 3 moles, with a prime value of 0.01 moles of water. From there, we can figure out the mass by multiplying by the molar mass of water. We look up here, we see that we have 2 significant digits here, 3 here, 2 over here, and 2 here. So our answer needs to have 2 significant digits. (1.82 times 10 to the negative 2 grams of water. It's a mystery where the questions are. Hey, number 3, 150 milliliters of 5 moles per liter hydrochloric acid reacts with 7.5 grams of potassium hydroxide. What mass of potassium chloride will form? So the first thing that we need to do is we need to create a balanced equation. So we've got hydrochloric acid reacts with potassium hydroxide in the solution. It tells us that this is going to be one of our products, but we can see from this double placement reaction that we're going to get potassium chloride. And it's asking us for a mass. Ooh. So we're going to want to put a solid in there. When I get this figured out. Alright. And again, I'm going to write water as HOH so that those who struggle can see the hydroxides here are going to be hydroxides here. And again, this is balanced out, 1 to 1 to 1 to 1. So now we can start with our next step of writing in our known information. And it's looking for the mass of potassium chloride. Calculate out our moles. Oops. Five times 0.5 moles per liter gives us 0.75 moles of HCl. Again, we're looking at now doing potassium hydroxide. You're going to divide by the molar mass of potassium hydroxide, which is 56.11 grams, for a value of 0.134 moles of KOH. Looking at the mole relationship in reactants only, we have 1 mole of hydrochloric acid to 1 mole of potassium hydroxide, and we have 0.75 moles calculated for hydrochloric acid, 0.134 moles. When we look at the rate that the reaction will occur at, we see that 0.134 is less than 0.75. That means that potassium hydroxide is going to be the limiting reagent. So we know that we can take these moles now of potassium hydroxide and follow through regular stoichiometry to calculate out the mass of potassium chloride. So we have 0.134 moles of potassium hydroxide, and there's a 1 to 1 relationship. Again, our given is on the bottom and our want is on the top. Now that we have our moles of our KCl, we can figure out our mass of our KCl by multiplying by the molar mass of KCl, which happens to be 74.55 grams per mole, to give us a grand total of 9.96 grams of KCl. Okay, number 4. Moving right along. 32.5 mils of hydrogen gas at SATP reacts with 0.02 grams of oxygen gas. Which reagent is in excess, and how many moles of excess reagent are there? So first things first, let's make a balanced equation. hydrogen gas reacts with oxygen gas, and we end up with water vapor. Balance out the equation. We have 2 oxygens here. We have 2 oxygens there, but now we have 4 hydrogens, so over here we need to put a 2. We now have a balanced equation. Let's write out the information that we know. Well, we know we have 32.5 mils of hydrogen gas at SATP. Well, we have the knowledge. 24.8 liters per mole. And here we have 0.0200 grams. And the question is, which reagent is in excess? So we need to calculate out the number of moles for each of the reactants. Oops. Making sure to convert your units. Zero point 0.0325 liters divided by our molar constant, is going to give us as soon as I turn my page over, a value of 0.0014 moles of hydrogen. Looking at oxygen, we have 0.020 grams. We're going to divide by the molar mass of oxygen, remembering that there's 2 of them. And we get a value of 6.25 times 10 to the negative 4 moles. So now we need to look at the mole relationship between hydrogen and oxygen, between the reactants. And what we see here is that there's 2 moles of hydrogen for every mole of oxygen. When we look at the reaction being consumed, we see that 0.0125 is less than 0.0014. Therefore, oxygen is our limiting reagent. So hydrogen is our excess reagent, and it has a value of 0.0014 moles. Moving on to question number 5. Which says in question number 4, which is the one we just did, what is the mass of water that can form in the reaction? Well, we know that our limiting reagent is the oxygen. So we can use the moles that we already calculated, the original amount of moles that we calculated, 6.25 times 10 to the negative 4 moles of oxygen. Now we need to go back to the reaction and look at the mole relationship between our given and our wanted. And our given is 1 mole of oxygen to 2 moles of water for a value of 0.0125 moles of water. From here, we can calculate out the mass of water. By multiplying by the molar mass. and we get a value of 0.022525 grams. And when we look back at question number 4, we see 3 significant digits in the volume and in the mass. So we have 2.25 times 10 to the negative 2 grams of water. Make sure when you go back that you take the original calculation of moles and not the number of moles that was calculated out in the mole relationship between reagents. You don't want to be using that 0.00125. It happens to work out, but it won't always be that way. Make sure you go back to the original value. Number 6. This looks good and complicated, but it's not. 10 liters of nitrogen gas at 105 kPa and 35 degrees Celsius are mixed with 33.5 liters of hydrogen gas at 95 kPa and 40 degrees Celsius, and ammonia gas is formed. What mass of ammonia gas will form? Well, first things first, let's start off with a balanced equation. Nitrogen gas is mixed with hydrogen gas, and we get ammonia. Now to balance this, we're going to need to come up with some kind of agreement here. We see 2 nitrogens here and 2 nitrogens, so we can put 2 here. We now have 6 hydrogens, so we're going to put a 3 there. The next step is to write down all of our given information. We have 10 liters of nitrogen gas at 105 kPa and 35 degrees Celsius are mixed with 33.5 liters at 95 kPa and 40 degrees Celsius, and it's asking us for the mass of ammonia. First things first, let's do some temperature conversion. We see that this becomes 308.15 Kelvin, and this becomes 313.15 Kelvin. Always making sure, if you're going to use the ideal gas law, to convert your temperatures. Speaking of the ideal gas law, PV equals nRT. This is how we're going to calculate out the number of moles. So N is going to be equal to PV over RT. Volume is 10 liters. R being the constant, and the temperature. Now remember, you need to do the math for the numerator and the math for the denominator, and then divide them, or you can enter in the numbers in the numerator, hit your divide sign, but make sure you're putting these two values in brackets. And you should get 0.4098 moles of nitrogen. Same thing for hydrogen. We have 95 kPa times 33.5 liters divided by 8.314. The R is the constant, times by 313.15. And you should get a value of 1.222 moles. You should be keeping all of your decimals. We're going to look at the mole relationship between the reactants. I have 1 mole of nitrogen to 3 moles of hydrogen. Writing out our calculated values. 2 moles of hydrogen. When we look at what's being consumed, we see that 1.222 is less than 1.230. Therefore, hydrogen is going to be our limiting reagent. So we can take the number of moles that we calculated out for hydrogen, and now we can go through and figure out the mass of ammonia gas that is formed. So we're going to take 1.222 moles of hydrogen. We're going to look at the reaction relationship between our want and our given. We have 3 moles of hydrogen, and we have 2 moles of ammonia. Gives us a charming value of 0.8149 moles of ammonia. Oh, that should be a 3. And then from there we can figure out our mass of ammonia. By multiplying by the molar mass of ammonia. .89. But when we look back up at the top, we see 10.0, 35 degrees Celsius and 40 degrees Celsius as being our limiting. So 14 grams of ammonia. Perfect. And bonus. What mass of sodium hydroxide will react exactly with 0.10 moles of hydrochloric acid? Well, first things first, let's build us a balanced equation. And we know that we have 0.10 moles of hydrochloric acid, moles. So we need to look at the mole relationship for sodium hydroxide to hydrochloric acid. We have 1 mole HCl and 1 mole NaOH equals 0.10 moles of NaOH. And from there, we're going to multiply it by our molar mass of sodium hydroxide. And we end up with 4.0 grams of sodium hydroxide is required to react with 0.1 mole of hydrochloric acid. Hey, sulfuric acid. Starting off with a balanced reaction. First we have to build it. Two sodiums, we need 2 over here, 2 hydroxides, we need a 2 over here, 2 hydrogens, and we're balanced. 0.10 moles of sulfuric acid. And we have 1 mole of sodium hydroxide. Oh, wrong. Sulfuric acid. I will be a pro at using this pen by the end. I promise. And we end up with 0.2 moles of sodium hydroxide. So from there we can figure out the mass by multiplying by the molar mass. And we see that we need 8 grams hydroxide. Okay, is C on this page? It is. First step, balanced reaction. Here we go. As you can see, I've gotten lazy and I'm not writing in my states, but you will not be lazy. You will pursue through this and continue to write states. OH. Starting off with 0.10 moles of H3PO4, phosphoric acid. Oh, we need to balance. We need 3 sodiums here. 3 sodiums gives us 3 hydroxides, 3 hydrogens, and we match. And we have 3 moles. So I'm sure by now you've seen a trend. Now that we've calculated out the moles of sodium hydroxide, we can now figure out the mass that we need to react fully by multiplying by the molar mass of sodium hydroxide. And we get, cheat sheet says, we get 12 grams. Okay, next page. In question 4, if there are 5 grams of sodium hydroxide, in which case will the sodium hydroxide be in excess and by how many moles? Alrighty. So, balanced equation. Hydrochloric acid plus sodium hydroxide gives us sodium chloride and water. And we happen to be a 1 to 1 to 1 to 1 ratio, so we're balanced, we're good. You will have written in states. You will not take up my lazy habit. So we have 0.1 moles here, and we have 5 grams of sodium hydroxide. When we look at the 5 grams of sodium hydroxide and we calculate out the number of moles we get from that, we're going to divide by the molar mass to see that we get a lovely 0.125 moles. We look at the mole relationship between the two reactants, between hydrochloric acid, which is 1, and sodium hydroxide, which is 1, and we have 0.10 moles here and 0.125, which tells us that the limiting reagent is going to be hydrochloric acid. And it's going to be limiting, and when it asks us by how many moles, this is an aside. This I don't expect you to do. Maybe I'll make it a bonus question on the test. Hint, hint. Okay, sulfuric acid. balancing out. We have a 1-2-1-2 relationship. This was 0.1 moles. This is still 5 grams. So we still need to figure out the number of moles of sodium hydroxide. We take 5 grams, we divide it by the molar mass. Again, we get this miraculous number of 0.125 moles. And we need to look at the mole ratio. There is 1 mole of sulfuric acid in the reaction to 2 moles of sodium hydroxide. We now see that 0.125 is less than 0.2, which means that sodium hydroxide is now the limiting reagent, and sulfuric acid is in excess. So if you were to make a prediction for phosphoric acid, I hope that you would think that sodium hydroxide would still be a limited reagent. And yes, I'm cheating and balancing and writing at the same time. We have 0.1 moles here and we have 5 grams here, which means that we have to figure out the number of moles. So 1 mole divided by 40 grams gives us, oh look, 0.125 moles. But the mole relationship has changed. We have 1 mole of phosphoric acid to 3 moles of sodium hydroxide. And we're looking at them being consumed, and we see that 0.125 is less than 0.3. Therefore, sodium hydroxide is the limiting reagent in this equation. Alright, that is limiting reagents in a nutshell.